Hi, in this video, I want to talk a little bit about the complexities of designing building foundations, especially for high-rise buildings in urban areas, and the general process that engineers go through to understand the engineering geology of the subsurface and come up with foundation design solutions which are safe, economical, and sustainable. You see, choosing building materials for the superstructure, that is, that part which is above ground, is much easier and more straightforward once the structural elements have been designed. Based on the architectural designs, the structural engineer can determine the loads in the structural elements and can easily select the appropriate materials to use for construction. The most commonly used building materials like concrete, steel, and wood have predetermined material properties. For example, the rebar used for concrete reinforcement has a known maximum tensile and yield strength, which is standardized across construction steel manufacturers. This is the same for the Portland cement and the aggregates used for concrete. This means that for a steel reinforced concrete structure, once the structural member loads, like the axial load, flexural load, and the shear load have been determined, the structural member dimensions can easily be designed, and the amount of concrete and steel reinforcement needed can easily be calculated. On the flip side, choosing the type of foundation is complex in construction projects. There are a couple of basic factors to consider that influence the choice and the design of building foundations, such as the type and the orientation of the loads from the structure, the type of soil, the soil bearing capacity, the environmental conditions, the earthquake susceptibility, and the ease of construction. This is the reason why geotechnics is the marriage between civil engineering and engineering geology. Both disciplines are branches of applied science, but there is a major philosophical difference between them. Geologists base their conclusions primarily on observations and intuitive reasoning, whereas geotechnical engineers measure the properties and apply mathematical analysis to reach to their conclusion. My name is Chido. I talk about geotechnical engineering related topics, including construction methods, disasters, and past, present, and future innovations in ground engineering. Please like and subscribe to the channel. With that, let's dive into the video and talk about the site investigation, geological modeling, and the selection of geotechnical parameters for foundation engineering. This is Geotechs with Clemens. It shouldn't come as a surprise that a thorough understanding of the ground conditions is a prerequisite to the success of a foundation project that is structurally sound, sustainable, and cost-effective. Generally, shallow foundations are usually the most economical foundation option compared to deep foundations. However, the selection of the optimum foundation structure is only warranted after the site constraints, the geological profile, and the properties of the various strata have been determined and well understood. Furthermore, good and sound engineering judgment is required to avoid running into costly engineering mistakes. A good example to point out is the Millennium Tower in San Francisco, which has gained the nickname the Leaning Tower of San Francisco because the building is experiencing a differential settlement and sinking in a tilted position due to poor foundation design. So, the importance of a properly planned and executed ground investigation cannot be overemphasized. This brings us to the aspects of foundation design and construction. The study of the site history is a good place to start. The information on the site history can be obtained from various sources, including plans of previous and existing developments, some aerial photographs, old topographic maps, together with geological maps and memos. This is important because useful information on the possible presence of old foundations, abandoned wells, and tunnels may be extracted from a study of the site history. This is especially important when a construction site is located on reclaimed land to establish the timing and the extent of the reclamation to help assess the likelihood of continuing ground settlement that may give rise to negative screen friction on piles, resulting in downward force that increases the loading on the shaft and reduces the bearing capacity of the piles. Furthermore, old piles and pile caps left behind in the ground from the demolition of buildings may affect the design and installation of the new piles. Engineers have to acquire detailed knowledge of existing structures and their foundations, and also the information on tunnels within and immediately beyond the site boundaries, the presence of sensitive apparatus within adjacent buildings, and locations of hospitals or other buildings having special purposes that may have specific requirements. This is very important because when installing a new foundation, ground lateral movements should be kept at a minimum to avoid interfering with the structural integrity and service provisioning of the surrounding infrastructure. Beyond the above-mentioned constraints, an understanding of the geology of the proposed construction site is a fundamental requirement in planning and interpreting the subsequent ground investigations. You see, foundation design is not a one-shoe-size-fits-all affair. What do I mean by this? Let's look at this geological map of Hong Kong. You can see that it is impossible to universally apply design rules without due regard to detailed geological variations. This is because the mechanical behavior of soil and rock varies depending on their geological formation. For instance, igneous rocks will exhibit a unique mechanical behavior compared to sedimentary rocks, and so will their weathered byproducts because of the inherent differences in their physical and chemical properties that stem from how the rocks were naturally created. Understanding the groundwater regime is another very critical factor for both the geotechnical and the construction engineers. The artesian water pressure and tidal variations can affect not only the design of the foundation and retaining structures, but also the construction process. Lack of groundwater information may lead to under-design of uplift pressure, especially for raft foundations. Moreover, unexpected and uncontrolled groundwater ingress may lead to construction site flooding, loss of equipment, and even loss of life. So, groundwater information is essential for designing the groundwater control scheme or dewatering program in the event that the project requires excavations below the water table to create a conducive work environment. Once the information from the desk studies have been gathered, the next stage is to execute ground investigations. You see, for a rational foundation design, it is very necessary to have data on the strength and the compressibility of the soil and rock at appropriate stress levels within the zone of influence of the proposed foundation. Other relevant parameters including permeability, such as for foundation works involving dewatering and grouting, and the properties of rock joints for the design of lateral loaded rock sockets. The ground investigations are conducted depending on the complexity of the ground and, to a certain degree, the form of the proposed development, the type of the structures, and the intended foundation types. Two test methods are usually implemented, with the first one being the in situ test and the second one being the laboratory test to complement the information obtained from the on-site test. The range of commonly used in situ tests includes the standard penetration test or the SPT, the cone penetration test or the CPT, pressure meter, plate loading, vent shear, the in situ permeability, impression packer, and some lightweight probes. Some of these instruments measure similar properties, but some are better than others depending on the soil conditions. For example, the cone penetration test has the advantage of continuously collecting the information on the properties of the soil. It is therefore more accurate in determining soil profile when compared with the standard penetration test. However, the cone penetration test is not suitable in ground conditions, such as in dense saprolites or gravelly soils where it may be difficult to advance the corn. One thing to keep in mind as a geotechnical engineer is that the state and the properties of the ground might change as a result of foundation construction. So, for high-profile projects, test driving or trial bore construction can be considered. This is when an actual full-sized pile is installed in the ground to the design depth as an investigative tool to prove the feasibility of the construction methods, the adequacy of quality control procedures, and to test for the load-bearing capacity. The laboratory testing is carried out on the soil materials obtained from the in-situ tests to help to characterize the materials and determine the relevant design parameters. These tests are grouped into two general classes: the classification or index tests, which involve the grouping of soils with similar engineering properties. For example, the particle size distribution, the Atterberg limits, the moisture content, the specific gravity, and the petrographic examination. I touched on some of these engineering properties in my previous video on road foundation geotechnics. You can go and check it out after this video. The second class involves quantitative testing, which includes the measurement of the strength or compressibility of soil. For example, the triaxial compression test, the direct shear test, oedometer or consolidation test, and the measurement of chemical properties of the soil and the groundwater. These standard laboratory tests will provide data on the design parameters such as the angle of shearing resistance, an important value used to assess the shaft and the end bearing resistance of piles, and in calculating the bearing capacity of shallow foundations. Furthermore, special laboratory tests such as the direct shear tests to investigate the behavior of the interface between soils and steel or soil and concrete may also be undertaken. Remember, the foundation doesn't work in isolation. It interacts the superstructure and the surrounding soil. So, analyzing these interactions is essential for an economical design, especially in complex case projects. Now, based on the mixture of the geological and geotechnical information collected during the desk studies and the ground investigations, appropriate geological models of the site are generated, which are an essential requirement for safe foundation design. They serve as a 2D or a 3D representation of the soil and rock layers and their properties. There are inherent uncertainties in any geological model, given that only a relatively small portion of the ground can be investigated, sampled, and tested. The ideal situation would be to conduct a large number of tests that are closely spaced, but this would be costly and therefore unnecessary. Finally, when selecting parameters to be used for the foundation design, a couple of factors are taken into account: the extent, quality, and adequacy of the ground investigations, reliability of the geological and geotechnical analysis models, the appropriateness of the test methods, the representativeness of the soil parameters for the likely field conditions, the method of analysis adopted for the design, and the likely effects of foundation construction on material properties. In principle, sophisticated computer analysis, where justified, should be based on high-quality test results. This is because the reliability of the output, let's say for finite element analysis, is critically dependent on the representativeness and the accuracy of the input parameters. All in all, when it comes to ground or geotechnical engineering, sound engineering judgment is always required in the interpretation of the test results and in the choice of the design parameters. As for me, this is why I find this particular field more interesting and exciting, because no project is the same and you always encounter complex challenges to solve. I've been your host, Chido Chasha. Please like and subscribe to the channel if you found this video interesting and informative. I will catch you in the next one. Thanks for watching.